What is that? Okay, so we're skipping those two opening questions just for the sake of time. Okay, we're talking about exponential growth and decay. So go ahead and start writing that out. All right, so here's our model. Our model for growth and decay. We've got f of t, sometimes this will just be an a, is equal to a naught e to the bt. So this little zero right here, which we call this a sub 0 or a naught, this is not we're not multiplying or dividing by 0. We're not doing anything with 0. All this means is at time of 0. So at our starting amount. So that's why that 0 is there, because 0 is where we start, right? When we measure something, we start at 0. It's the same kind of concept there. All right, B is going to be our growth or decay rate, this value right here. So if B is greater than 1, then we have a growth rate. If B is less than or equal to, if B is between 0 and 1, then it's a decay. We shouldn't have any negative B values. Okay, and this equation can be used for any kind of growth or decay. This is the default equation. All right, so it says the graph, which is in your textbook, but you can look up the graph if you really want to. The graph shows the U.S. population in millions for 5 selected years from 1970 through 2010. In 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. And it says find an exponential growth function that models the data for 1970 to 2010. Okay, so we are trying to write a function. All right, keep that in mind. Our end goal is to have a function. What I usually do is I like to write out my equation just so I have it handy that I'm using. And then I write out, okay, f of t, a naught, b, and t. All right, so A naught is our starting population. So what's my starting population according to the problem? 203.3. That is in millions, so we'll have to remember in our final answer to put our answer in millions. Ooh. All right. Is there any indication of B, our growth or decay rate? Usually given as a percentage or something like that. No. So that is what we are looking for. What is my T? Chase?
Is it 40?
It is 40. How'd you find 40?
I did 2010 and subtracted that by 1970.
Good. So we are trying to find over 40 years, what is the population? All right, and then F of T. Any guesses as to what F of T is?
3087.
308.7. Good. So that F of T is our value, our population in this case, over time. So this is our population given a certain time, and this is after 40 years. So let's go ahead and plug all that stuff in. So I have 308.7, I'll zoom in, equals A naught, 203.3, E to the B times 40. Okay, so I need to solve for B. In order to do so, I need to divide both sides by 203.3. So I'm just going to leave it as 308.7 over 203.3 because I'm going to get some nasty numbers. I'm going to go ahead and write this as 40B. And then how do I get rid of that E? What?
I think I said something else. Natural log.
Natural log both sides. Good. So when I take the natural log of both sides, I'm left with ln of 308.7 over 203.3 equals 40B. And then I'm going to divide both sides by 40 to get my answer. So go ahead, type that into your calculator to find what B is equal to. Chase?
I got 0.01.
Good. So we get 0.014 something, something, something. We'll just write it as 0.01. I don't know why I put the 0 there. Okay, and then, but we are looking for the function. So I need to write out my function using A naught, B, and A naught and B. So my final equation is going to be f of t is equal to 203.3 e to the 0.01 t. So that right there is my function for, is it population growth? Yeah, the US population. All right. So now this is our growth function. So now what we can do is we can use it to find, okay, what is it going to be in 2021, 2022? Or we can do it the reverse way. So in this question, it says, by which year will the US population reach 335 million? So we can use this equation right here to determine when that population is going to be 335 million by plugging that in for f of t and solving for t. So go ahead and solve for t. We'll come back to it in just a second. All right, someone help me out. What do I have to do first? What do I need to solve for t? Yeah, Kayla? Perfect. Divide by 203.3. I'm going to leave my value just like that, just so because we're dealing with really small numbers, we don't want our rounding to be too far off. So I want to keep that value. Okay, then what? Someone other than Kayla. Tegan, what do I have to do? Ellen. So I have ln of 335 over 203.3 equals 0.01 t. Divide both sides by 0.01. And what is t equal to? Let's round to the nearest year. 50. So after 50 years. Now, the question specifically asks, what year does it reach 335 million? 50 years does not answer that question. So how do I find what it's going to equal or what year it is? Madison?
Add 50 to 1970.
So in the year 2020, so last year, the population should be, yeah, that's it, 335 million. Now, I looked up the population earlier today, and the population for 2020 was 331 million. So what are some things that could make this specific problem? They actually change the equation every year just because it changes so much. But what are some things that could have changed it, Chase?
A pandemic.
A pandemic definitely could have changed it. We lost some people last year, unfortunately, to COVID. That's a real thing. We lost a lot of people that way. Probably not millions. Well, yeah, maybe millions. Okay, what else? What's another thing? What's another thing that could have changed the population?
Different generations have different plans in mind, like having kids and stuff. So
Yeah, for sure. So like in 1970, people were having like 6 kids or 6, like they were having a ton of kids. But both my parents are one of 6. So, and then they had 3 kids. So yeah, that's reduced a lot of people. Also, people just aren't having kids, period.
Yeah, I was gonna say, if you think about like the social and economic climate, and the war on terror sparked up around the 1980s, and then forward, people stopped having kids as much as well.
Right, yeah. So when this, in 1970, there's a difference in that whole thing, yeah.
how we handle immigration.
How we handle immigration? Yeah, that's another thing. I didn't even think of that. So people coming into the country is also a huge thing. So yeah, for sure. So those are a few things. Of course, we know that our equations aren't like perfect, but give or take a few million, it's pretty close to the real thing. So, but they do change that equation every so often. So they come up with a rate of growth, and it changes every so often just so that we can have a more accurate depiction, but they do change it pretty often. Okay, cool, nice job. Let's talk about logistic growth models. So I'll zoom in on this equation. The model for logistic growth is given by C over 1 plus A e to the negative BT. A is greater than 0, B is greater than 0, and there's the growth constants. And then C is going to be our horizontal asymptote. Okay, Miss B made a bit of a boo-boo. Right here, this first problem, it says the function, it gives this equation. This should be the function right here. So go ahead and write given. That way you're like, where did that equation come from? This is the equation. So it's 3,000 over 1 plus 20, sitting at negative 1.5 t. I don't imagine that you're able to just come up with this out of the blue. So 30,000. I've been saying 3,000 all day. It messed me up earlier. Okay. All right, so it says that this function describes the number of people, f of t, that become ill with coronavirus t weeks after its initial outbreak in a town with 30,000 inhabitants. Okay, and it says how many people became ill with coronavirus when the epidemic began. So in order to find the number of people that were ill when the epidemic began, what am I going to put in for T?
0.
0, yeah, because my time is 0 when it starts. That's what we want. So let's go ahead and plug in. We're going to find F of 0. And that's 30,000. Did I write 30? Yeah. 1 plus 20 e to the negative 1.5 times 0. Now, negative 1.5 times 0 is 0, and e to the 0 is 1. Anything to 0 is 1. So e is no different. So you can type 30,000 over 21 in your calculator and tell me what you get. What'd you get?
10,007. Did you want a decimal?
I do want a decimal. And we don't have fractions of people because those people aren't alive anymore.
1,428.
Are you sure about that?
Well, you can.
We'll round up.
You can just make.
That's fine. We'll round up. They're almost.
Did you say you can just?
What?
I mean, like, artificially.
Shh. All right, let's not go there. Okay, so at the beginning of the epidemic, 1,429 people were infected or ill. Okay, so T is week, so let's find out how many people were ill by the end of the 4th week. So find F of 4. This is where I want to kind of instruct you guys on how to type it into your calculator. It sounds silly, but man, you'd be surprised, I think. Okay, so when you type this in, you're going to do 30,000 divided by 1 plus 20 e caret negative 1.5 times 4. And you need all the parentheses where I put parentheses. Because we want to divide this whole thing, so we have to put parentheses around the whole denominator. And then we want e to this whole thing, so we have to put parentheses around that as well. Otherwise, what it's going to do is it's going to do e to the 1.5 and then multiply that whole thing by 4. And then if you don't do 3,000 divided by parentheses the whole thing, it'll just divide by 1.
So here's my question. If I type it in exactly like it is up above that one.
Like
well,
this?
I still need, yes, but if I type it in exactly like that, with the vertical fraction bar and everything like that, well, I still need all those parentheses.
No, on the fancier calculators, it'll let you type it in just like that usually.
Yeah, okay.
But if you have a red calculator, it won't. So you have to type it like this. Fancy calculator, you can do that. Red calculator, that. Can you hold it for like 10 more minutes?
Sure.
Yeah.
So what do you get? What is it? 38,000?
28,000.
Oh. Okay, and make sure you label with people. Okay, so that's how many people are affected at the end of the 4th week. It's a lot of people in a month. Okay, so this asks, what is the limiting size of F of T, the population that comes ill? So limiting size is what's the limit? How high can it go? How many people can be infected at most? How do you know it's 30,000? Well, yeah, how do you know it's 30,000?
That's the whole population.
Yeah, so I only have 30,000 people. No more than 30,000 people can become infected. So 30,000. Fresno was calling me. 30,000 people is the limiting size. And we know that because that's the max population. We can't go any higher than that. And then also note that C is equal to 30,000. Okay, so that numerator right there, that is always going to be the limiting size. Okie dokie. Okay. Let's look at another type here. Got Newton's law of cooling. I think this is the last of it. Yeah. There's like one small thing in a second here. Okay, so Newton's law of cooling, the temperature of a heated object at a time t is given by T equals C plus T naught minus C e to the kt. So C is going to be the constant temperature or the temperature of a room. So like in here it's, I don't know, probably 70. Okay, then your T naught is your starting temperature of the object. C, still the same thing, temperature of the room. E is just a constant. K is going to be the rate at which it's cooling, and T is the amount of time, and it'll say minutes versus hours or whatever. It's gonna, your rate's gonna be different depending on what the time is. So, and then this T over here is our ending temperature. Okay. The cake removed from the oven has a temperature of 210 degrees Fahrenheit. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. After 30 minutes, the temperature of the cake is 140 degrees Fahrenheit. And so we want to find a model for the temperature of the cake after T minutes. So I'm going to go ahead and write out T, C, T naught, K, and baby T. I'll tell you this much. We don't know what K is. We are trying to find the K, the constant of cooling. So, what is my T? What is my starting what is my ending temperature? I don't think I read the problem, did I? A cake removed from the oven has a temperature of 210 degrees Fahrenheit. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. After 30 minutes, the temperature of the cake is 140 degrees Fahrenheit. So which one of those values is the cake's ending temperature? Ben? 140 degrees. Thank you. All right, what's the constant temperature? Madison?
70 degrees.
70 degrees. That's the temperature of the room. It's not changing in this case. So like you can change the temperature of a room, but when you're baking a cake, it's going to stay the same for that amount of time. Your T naught, so our starting temperature, Lily? 210. And then what is my T for time? 30. Okay, let's plug all that into our equation. So I have 140 equals C plus T naught minus C e to the K times T. Let's go ahead and simplify. So I have 140 equals 70 plus 140 e to the 30K. So we're going to solve for K. If we subtract 70 from both sides, I have 70 equals 140 e to the 30K. Divide by 140, I get 1/2 equals e to the 30K. Just divide both sides by 140. If I take the ln of both sides, I'm able to find or get rid of that e. So ln of 1/2 equals 30K. Divide by 30. And what is K equal to? Lily?
Negative 0.023.
What do you say, 23? Good. Okay, so we still have to find the model, which means that we're trying to find the equation. So we'll write it out as, I'm gonna sit down here. T equals 70 plus, we'll just write that as 140. 140 e to the negative 0.023 t. And that is our equation for our temperature after a given time. So let's go ahead and find what the temperature is after 40 minutes. If you're using a red calculator, make sure you put parentheses around that whole exponent. All right, and when you get your answer, go ahead and round your answer to the nearest degree, like temperature degree. So whole number. What do you get? You're good. So we'll round that to 126 degrees Fahrenheit. All right, if we want to find the temperature of the cake, we just do the reverse like we did before. For the sake of time, I'm actually going to skip this part and you guys can do it for review and I can check your answers. All right, so expressing an exponential model in base E. So if I have this function here, what I can do is I can take my B, and what I'm going to do is I'm going to write this as y is equal to a e to the ln of b times ln of b times x. Okay, so all we did was we took that b and put it in the exponent. Because what ends up happening is this e and this ln cancel out and those come down. But when we write it in this way, so I'm going to actually pause my thought. I'm going to take this equation, rewrite it. So I can write this as g of x is equal to 2.577 e to the ln of 1.017 x, like that. And what that does is it shows us that we have a K of 1.017, or sorry, of 0.017. So if I have, what this 1.017 is it's growing by 1.7%. So if I take this away, it's growing by 1.7%. And the way that I'll kind of explain it, so go ahead and write out that this has a growth rate of 1.7%. But the way I'll explain it is if, let's say, we go out to dinner and we spend $9 on our meal. okay? And we want to know what our total is after tip. So let's say we leave a 20% tip. So what we're doing is we're multiplying this by 0.2, then we're getting 0.18, or no, 1.8. And then I take that 1.8 tip and I add it to my $9 and I get 1080 as my total, right? What I could have done initially was done 9 times 1 plus 0.2, because when this distributed, this is 9 plus 1.8, or 9 times 1.2. So what you're doing is you're saying, okay, it's a 20% growth rate of what my total was. So if I had $9 and then I multiply by the growth rate, that's how much total I'm going to pay. It's kind of the same concept here. So we wanted to make sure it's a growth rate. It's growing by that 1.7%. All right, so that's all for you guys today. There is no homework assignment. So